All right, welcome back to the Green Ninja Climate Science series. We're going to be transitioning here from a little bit of kind of Climate Science 101 videos to more like frequently asked question type videos. So our first kind of frequently asked question is, how can there be global warming when last year was so cold? And so I don't literally mean last year, but I just mean at any given location, wherever you might live, you may experience a month or a few months or even a year or longer that was pretty cold relative to your average, in spite of the fact that the world's temperature has increased pretty substantially. So I want to kind of ask or look into why this can be the case. So to set this up, I want to show you another graph of globally averaged surface temperature over land. This is from the Berkeley Earth surface temperature data set. And so what they're showing here is from the 1750s to the 2000s. We've seen an increase in temperature of about 3 degrees Fahrenheit. But I want you to notice the difference between the red line, which is a 10-year moving average. So each single dot on here is an average of 10 years total, versus the 12-month moving average, which is showing you the average, for each given kind of year, or a moving average for each year. And so what you see is that we have these wiggles from year to year in the globally averaged surface temperature, and this is mostly due to El Nino and La Nina conditions, which we won't really get into. But you can see that the wiggles in the globally averaged surface temperature over land are relatively small compared to the overall increase in temperature. So just to take an example, the coldest years in the 2000s were still warmer than the warmest years in the 1980s, because the rate of warming of the long-term warming is a lot larger than the year-to-year variability. But what happens is this is not the case at any given location where you might live. And so this gets to the point of why given locations can be cold in spite of the globe getting warmer. So just to give you an idea of how this works, let's just take a very kind of basic cartoon look at the Earth's surface. So let's say this is water here, and we have some continents here. And let's say that you live right at this point. So nobody lives in the global average, right? Everyone just lives at one single point on the surface of the Earth. And so if you live here, your temperature is not every single point on the Earth is the same temperature as the global average, right? So what happens is your temperature is controlled by the way that cold and warm air masses might be moving over your given location. So let's say that right now the Earth's temperature, what you're looking at, is 60 degrees Fahrenheit. In this cold air blob, let's say it's 40 degrees Fahrenheit, and in this warm air blob, it's 80 degrees Fahrenheit, and the rest of it is 60 degrees Fahrenheit. And these approximately equal each other, so the average is 60. Now, what's going to happen at your given location in terms of temperature if these air masses start to move around, which is actually what does happen in the real Earth system. So we have cold fronts and warm fronts, which are just cold and warm air masses moving around the surface of the planet. So let's say that the cold air moves to the south and the warm air moves to the north. So first, the warm air moves over your given location. So you went from 60 to 80 degrees, and now back to 60, and now the cold air moves over your location, so now you're down to 40 degrees. So your given location experienced a big swing in temperature over that time period. But what happened to the globally averaged temperature here? Well, nothing, right? Because I didn't change the shape of these two air masses. I'll just say for the sake of argument that the temperature stayed exactly the same of these two air masses. So what happened is I just moved them around, and so if you average over the entire surface of the planet, you don't get any change. But at any given location, like at this location, you did get a big change. So what you see when you look at the graphs of surface temperature over time from any given location is you can have really cold years in spite of the fact that the globe may be really warm. So here's an example of that from 2010. So 2010 was the warmest year on record in the instrumental record. And what this map is showing is locations on the globe that were above average and locations of the globe that were below average in terms of temperature for 2010. So keep in mind, 2010 is the warmest year on record in the instrumental record, so going back to the 1800s. But that does not mean that every single location on the surface of the planet was warmer than average. So if you look at central Russia and Mongolia, you look at Europe, you look at central Australia, you look at parts of South America, you look at Florida, those areas actually experienced colder than average temperatures, despite the fact that the globe overall set the record for the warmest temperature on record. And so another way to look at that is in terms of time series plots at given locations. So remember, here's our graph of the time series for the globally average land temperature. And just to remind you, we saw an increase of about 3 degrees Fahrenheit overall since the 17 and 1800s. But now let's look at a graph from a given location. So let's look at Washington, D.C. Now, what you'll see here is that Washington, D.C. has experienced about the same amount of warming relative to the 17 and 1800s as the globe has. It's basically increased by about 3 degrees Fahrenheit in Washington, D.C. Over that time period. However, when you look at this 12-month moving average, these wiggles are way more intense than at the global average. And this is because of this issue of warm air masses and cold air masses moving over your location at any given time. So what this means, going back to our question of how can there be global warming when last year is so cold? Well, let's take a look at right here. This might be, say, 2008 in Washington, D.C. That year was relatively cold compared to the years in the late 90s and early 2000s. And it was even cold relative to years in the early 1900s. Say like in the 1930s perhaps, it was a lot warmer than in 2008 in Washington, D.C. And it's because of this issue of warm air masses and cold air masses kind of moving around the surface of the Earth and causing weather at any given location. So it's kind of harder to see the increase in temperature at any given location than it is to see the temperature increase in the global average, because when you average over the globe, you essentially get rid of this movement of air around the surface of the Earth that causes these intense wiggles and kind of obscures the global warming signal. So this isn't just the case with Washington, D.C. When you look at all sorts of different places around the surface of the Earth, you see that overall the temperature increase in Mumbai and Sydney and Dubai and Rio de Janeiro is around 3 degrees Fahrenheit, just like the global average. But the noisiness of the data, the wiggles in the data, are a lot higher in any given location than they are in the global average. So it just means that wherever you live, you're perfectly capable of having a pretty cold year, any given year, in spite of the fact of long-term warming. And it doesn't mean that your area is not warming. It just happens because cold air can move over your location for a long period of time. It could be just a couple days. It could be a couple weeks. It could be as long as a year where you have colder than average weather. And it really doesn't mean anything unless you come up with a data set like this and see, okay, how is the long-term change in temperature reacting? You can't just pick out any given year and draw any conclusions from that. So hopefully that helps explain a little bit how any given location can have a cold year, and it's not inconsistent with the idea that the globe is warming or even that your location is warming in the long term.